Thanks for watching my video. I'm planning to make a series of videos to talk about memory management, and I will provide coding examples of using the standard classes, how a good program, a modern C++ program, should make good use of memory to avoid memory leaks. Here will be the outline, and the first class should be mentioned will be the allocator, the standard allocator. An allocator is allocating system memories or system resources in raw pointers. Example, and it generally providing a allocate and deallocate method to it for a type and returns and work with a raw pointers. If it's allocating a system memory, it might be using the built-in, using the operator new or delete, or might be using malloc or free, which is from the C APIs. And it's also possible to use the allocator to work with a non-heap memory, for example, a stack memory, to provide very much better performance if the memory block if the allocating memory is not huge. Yeah, this is could be provided as a way to work with the standard containers and to boost the performance. And it's also possible to use the map memory, which is actually a virtual memory and bound to a file which is very similar to a system swap file, and highly worked with the system virtual with the operating system virtual memory management. And then it's not recommended to directly use a raw pointer in general, because it's risky of memory leaks. So the standard library provided smart pointers to us. For example, the unit pointers, the share pointers, and weak pointers. Weak pointers are used with share pointers. So today I'm going to demonstrate the unit pointer and share pointer usage, and also demonstration of weak pointer, how to use the smart pointers, which is defined by the standard libraries. And I may also involve some examples of using allocator, because allocator is actually it's actually simple, I think. So let's go. Well, first of all, involving memory management in C++, we have to include the memory header First, let's define a example class. To demonstrate the usage of the allocator and the share and the smart pointers. And first of all, let's try to define a allocator of the example using example allocator. In this case, there's also another trade class, allocator trade class. Could be used for programmers to it could be used as a convenient class to work with the allocators. We will go through this if possible later on. But for now, we are going to use the unique pointer. A unique pointer should be used in a scope like like in a function scope, and the lifetime of the pointer is exactly the lifetime of the scope. For example, when the program exists, returns in the main function, the lifetime of P1 terminated. And you can also use it in a class scope as a member. For example, P1 in1 I1. Okay. For example, I1. So in this example, as a I1, when the class is destructed, the lifetime of I1 is terminated. So these tools are the best example or best places to demonstrate how well the best cases for using the unique pointer. Unique pointer cannot be copied, but it can be moved. If you want to pass it to a function, for example, a function unique pointer. Let's say we want to pass a unique pointer example to a function. You cannot pass a copy to the function, but you can pass a reference. You have to make it a reference. To it is better to be const reference and make use of the P. And you can also do a move pass in a move semantic. This is a move semantic and not copying the P. So let's see. We create an example here. Well, this is a Raii pattern in C++. This is very important, very important pattern. Resource. I will talk about Raii later. Important. This is very important. I will go back here and talk about the Raii later. So, if you want to pass the unit pointer to a function that wants to use the unit pointer, you have to pass it as a reference. A good suggestion is passing it as a constant reference. Or you can move it. You can move it to the function. It's very important to remember that when you move an object, when the pointer is moved, it will no longer be available in the next line of the context. So P1 in this example, P1 will no longer available. So don't use it again. So here, starting from this point, P1 should be T1 should be now. So you can use that. You can use it again, and you can safely discard P1. So okay, let's see. Yeah, in the example, you can use it as like you are defining here. For example, we say int. Maybe we get the int value, right? Get int. So we can safely use the pointer here. If IP is available, then we print out the for example, we print out the value. Example int would be IP. This is an example here. And in the second example, it's very similar. But remember that in the second example here, in this function, the lifetime of the pointer of the unit pointer is the same as this function. So when it returns, the lifetime gone, the lifetime of P is terminated here. At the end of the function. So this is the difference when you're passing a unit pointer to a function. In this example, the lifetime never changed. It's not changed when the function is returned. And in the second example, when you are using the move semantic, the lifetime of P of the instant is done, it's finished at the end of the function when it's returned. So this is the basic usage example when you are going to pass the unit pointer to a function. So when you are working with a member, a class member, for example, in this way, the lifetime of I1 is the same as P, as the example. So, for example, we give it a constructor here. Let's say we take it. Okay. We take another. Okay. This is the. Let's make a move semantic constructor here. I want and move. Let's say we have to forward the pointer to the unit constructor so that it can take over. It can take over the ownership of the int here. This is a very important pattern. You can construct it from a move semantic unit pointer. So we can forward the unit pointer from the move semantic, which is the R value, right? R value. This is called R value reference or Raii value reference. This is the move semantic. So this is one way, I should say suggestive way to construct a unit pointer if you use it as a member. Let's make it an explicit constructor. And you can also use a copy. Let's try this. This is different one. This is the copy semantic. let's see what will happen later on as a comparison. Or you can construct it from a raw pointer. But I will suggest this way. I will suggest the move semantic constructor. If that's part, if your compiler supports move semantic, it supports the R value. So this is the suggested way, but this is not it. For security reason. Okay, let's see. So we have to change it. For example, a new in 1. Okay. Okay, let's see how it runs first. Okay, let's see what's happening. Code to implicitly deleted copy constructor. See, this one is not allowed. Copying a unique pointer is not allowed. It's deleted, disabled. So this is not working. This is an error. Okay, let's try again. Oh, alright. We have to include the IO stream library. Let's see. Example int 1. Okay. Okay, let's give it the name of the function. So that our example will be easier to read. See, use unit pointer. Example int is 1. So this is the. Let's see here what the pointer has become. See, this the value is not changed. The value is not changed here, but actually in this, starting from this point, P1 is no longer should never be used again. Let's look at the value. The value is still looks like a valid value because we didn't change it in this function. In this function, we may change it. We may say that P is okay. Let's do this. Let's try this. Before move. Let's see what's going on. Oh, let's compare. Okay. See, P1 before moved. P1 after move. The value is not changed. But actually, you should never use P1 again here. I mean, you can never dereference the. You should never dereference P1. But dereference, it means the P1 or P1 like this. You can never do this. Do this after P1 is moved. Well, I can actually do a reset here. Let's see what will happen again. Explicitly reset it. See, it became null. It became null. It became a null value. It became a zero. Became zero. So the move semantic is like when you move an object to a function into a function, you give up the ownership. You give up the ownership of that object. And inside it's up to the function, it's up to the collect function whether it's going to reset it or not. If it's not resetted, the value might not be changed, It should be changed. It should be clear. It should be reset. It should be reset for a move semantic. It should be reset. But if you not, the value may be not changed. So it's up to the implementation of the class, of the unit class. So this is the unit pointer. Okay, I will move it into a separate function. Okay. Unique PTR example. Okay, now I'm going to continue with the term Raii. Raii is a Raii means resource acquisition. Ra means resource acquisition. Is a initialization. Resource acquisition is initialization. This is this pattern. Here we have two Raii pattern. The first one is to the unique in pointer here. And the second one is the example unit pointer. So when we call generally when we allocate a raw pointer, in this case we use a new operator to allocate a raw pointer. In this scope, the raw pointer is not saved. If you when we handle immediately the raw pointer to a smart pointer, like unit pointer. Like a unit pointer here. in this example, the new int raw pointer is handling it is moved to I immediately. It's moved to I immediately. So it's saved. This is called Raii, which is initializing the unique int pointer here, which is called Raii. Make the initialization to acquire the resource immediately. You just allocate it from system resource allocation routines like operator new, or any other C API. For example, you can actually do something like this. For example, a file pointer, and you can say that it's going to be deleted using a file and P2. Let's say it's P2. So the second one is special. We pass the second parameter, temporary parameter. This is called the delete function. It's actually a, let's see. Let's call the open function, for example, dv random, just for example, read it. We just want to read it. Okay. At the binary, and the constructor here changed. We need to pass it a second parameter, which is the fclose. Oh, not calling. So here, this is the second one is more interesting than the first one here. The fopen here is very similar to the memory, the operator new, which is instead of allocating a memory block, it's allocating a file handler, which is a system resource. And when we acquire the system resource from the fopen routines, we handle it immediately to the unit pointer. So it's saved. This is called resource acquisition is initialization. So we make the initialization of a constructor. In this case, for example, the unique PTR constructor, the initialization. Let's ban the resource acquisition. When we open the function, when we open the file, we handle it immediately to the constructor. This is Raii. And the destructor of the unique pointer will take over the responsibility of closing the file, and the close routine is here. Is the second parameter we pass to it. So this is a very important usage of a unit pointer. This is very important usage example. Let's try. No matching function. Let's see what's happening. No matching constructor for initialization of unit. Okay, let's see. Okay. Destination is here. It retains an int. It retains an integer. Right? Retains an int. See? Let's try it again. Yeah. It's okay. It's okay. So remember this. This is more important. This is the second one is more important and more interesting. Use example of a unit pointer. Okay, let's move on. Move on to share pointer. Let's see. Share. Let's make a share pointer. Example, usage example. Share pointer. Okay. A share pointer can also be used in a scope lifetime. For example, in this function, we can also use share pointer, but it's not suggested to use it for scope lifetime. It's highly suggested to use unit pointer for scope. For scope instead. Generally, when we are using a share pointer instance, just like the name suggested, it needs to be shared. By share, it means that we share it with another routine, a long-term routine, another object in another time space, and it coexists. We use it in this space, and allowing another space to use it at the same time. So let's make an example. This is the same Raii, but share. So it can also be a I2, which is share. Which is shared. What's that? Okay. So let's see. We can pass it to function anyway. We can pass it to a function as a reference. As a reference like this. And we can also, it's suggested to be const. And we can also pass it as a copy. This is copy the ownership, shared ownership. So this is different. Unit pointer cannot allow this, but in share pointer, it's possible. It's possible. If you are not going to make a share, you're just temporarily passing the pointer to a function. It's highly suggested to use this form, the first form. We can say that just like this. We copy the example here. Well, on the usage side, the code should be a little bit different here. When we get a pointer, when we get a share pointer, it should not be used directly. It should be code like this, p IP, let's say p. We need to lock it. This is very important. This is very important, especially in the second one. I mean, especially in this one. But in the above, in the first form, it's generally fine. It's generally it's fine to use it directly. But in this form, we have to lock it. This is important to use a lock here. And if it's locked, then we can use the IP here. Yeah, please take closer look at these two, at the difference of these two. In the first form, we can use the p pointer, use the share pointer directly if we pass it to a function in a constant reference, as a constant reference, because as the semantics suggested, if we pass the share pointer as a constant reference, the lifetime of p is highly restricted to the same lifetime as in the routine, as in this routine. So yeah, it's safe here to use it directly. But in the second form, when we pass it as a share ownership, we have to code a lock. So because at this point there's no guarantee for p to be valid, which means that at this point, I mean at this line, p might have been destructed already. So we need to lock it. So we need to lock it. If there is an instant, if there is an object being logged, then we can use it in this example. So this is the difference. This is very important difference when using a share pointer. When using a share pointer, if you are sharing it with another a thread or with another object or routines. So this is very important. This is critical important. Remember this. This is critical important. Okay, let's try to run it. Okay, let's see. No member named. Okay, oh, okay. It's not. It's not a P. It's not a. It's not an arrow. It's a dot because the log method is is belonging to the share pointer object. When we are using an arrow, you point to an example, and the example has no such lock method. So let's try again. Let's see. Oh, okay. Let's see the header. Okay, it's from weak pointer. Okay, I think I'm wrong. I'm wrong. Okay, let's see. Okay, this is not. This is wrong. This is wrong. This is not like what I'm saying. It's belonging to the. It's weak. Okay, forget this. This is wrong. If it's a weak pointer, we need to lock it, but share pointer does not need to lock it. So this is the difference. Okay. So we can actually use it the same way as in here. It's safe. It's safe here. The same here. See, share pointer example one. Okay, let's go back to this case. When we should use this case, it's when we are using a weak pointer. A weak pointer means that we are using the object but not taking the ownership. Using example without the ownership. So in this case, we have to use the lock. We have to use lock method. So this is what I said. At this point, if you are passing a weak pointer, to a function, and at this point, there's no guarantee for P to be valid. So and we can try to lock. This auto is actually a share pointer. We can try to lock the ownership here. Lock the ownership. So we need to. So we have to lock the try. We have to try unlock the, try to lock the ownership. Try to lock the ownership for usage. This is very important. This is very important when you're using a weak pointer. So let's see.
It's 21 hours.
P1. Let's say 3 to ensure it's calling the weak pointer 1. 2. Let's see. Invalid operands to binary. Oh, right. This is not, this is an, yeah, we have to go. It's not a IP, let's say it's SP, and right, and it's SP, IP, because IP is actually a share in, I share in here, IP. If we lock the share pointer, we get the integer value. Yeah, let's try again. Let's see. No variable conversion from n to, okay. 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 1, 2, 3. Number 1. What's happening? Okay. Do you see? 1, 2, 3. 1, 2, 3. So this is the usage of share pointer and weak pointer. Weak pointer is a weak share, weak ownership, weak shared ownership. So this is 3 class for using smart pointer. A weak pointer can also be a member, but you have to, it's the same. If you want to use it, you have to check the ownership. You have to check the ownership. Okay, let's see. Let's make a, okay. Let's see. And it's possible to do something like this. For example, weak shares, which is no ownership. Okay, no ownership. So this is the example usage of the 3 smart pointer, coming from the standard library. And you need to include the memory header to use these smart pointers. And the key point is the Raii pattern. Raii pattern is very critical. It's very important in C++ programming. So you have to avoid using raw pointer directly in any cases if possible. If you don't have a smart pointer, You can also write your own Raii handle class. For example, a file handle here. You can explicit take over the ownership, take over the handle immediately here, and then in the destructor you explicitly call the close function. Close. Okay. If file is valid, we can give it a default value. But this is very special. This is required C papa 17 or C papa 20 or C papa 2A, C papa 2B. Okay. So this is an Raii example. Raii file handle. Let's see. Let's try. Put it in here. So example, let's say FH, and give it see. If we define our own file handler instead of using unit pointer a file in this form, we can make it optimized without passing a close function, because the file handler is defined by us, so we know that it's going to call the call here when in the destruction. So this is a simple example of Raii, and Raii is very important in C++. So okay, I will explain why it's important in Raii. So let's first try to run this after we add the file handle. Try to write the example. See, so it works well. So I will design an example to demonstrate why Raii is very important. I will design an example. Okay. So Raii is let's say okay. In this function, I will show why Raii is important. Let's use the file handle. Use this example. Again. So why Raii is important. I will explain. So here, anytime when we allocate when we create a function, open a file from the C API from the system. Here we immediately pass the file handle, the raw file pointer, file handler. To the file handle class, and then which means that we hand over the ownership and let the file handler, let FH to take over the ownership. And at the destruction here, we ensure that the file can always be closed. Why this is happening? Let me explain. Say here in this, we are calling some function here. Say, okay, let's see. Use file handle for writing something here. Let's say let's try such a function here, and we pass the file handle reference. We pass it as a reference. Okay, pass the reference to it. Fetch to the function, and we make use of the function here. Let's say write the code later on using fetch for writing. It seems that it's a code. And notice that this function may raise an exception. So here, this could raise an exception or cause or any or my simply abort the program. So this is the reason. This is very important. This is the reason why Raii can help us to avoid leaking the file handle. This is very important. For example, we may throw an exception here. So let's include let's say throw a runtime. So a runtime error, okay. Expected error. So in this case, this function raise an error, So if we are using fh to do more jobs, if we are using the file handle to do more jobs here or whatever, no matter what error is raising here, it's safe. We're sure The II ensures that the file handle is safe, will be safely deleted, will be safely closed anytime, in any cases. Here we catch the error. Just ignore it. Let's see. Here. Okay, let's check. Let's see how to examine whether the file is closed or not. It's safe here. Let's add some diagnostic some code here to examine whether the file is closed when an exception is raised. If it's closed, let's say file is closed. File closed. Let's see. Okay, it's not code. So there is a leak. Let's see what's happening. Well, the expected output should contain this code, should contain this line file pointer is closed, but it's not. So there is an error here. Let's see. This IR is code. What if we are not coding? Not code again? Not coding either. It's not code. Interesting. Okay, the file open is not. It's not opened. Let's see here. Maybe the file is not found here. Let me check. Random, there is the random here. I guess the file mode is incorrect. Let's see. My guess is the file is null, right? See, file is null. So this open mode is incorrect. Maybe we don't have a permission here. Let's see. Let's create a text file. Just a text. Just the source file itself. Interesting. Why is not opening? Why it's not opening the file? Why the file is not? Error stream, right? Let's see, error num. Error num is 12, 20, 22. Error stream, right? Error stream. String invalid argument. So the argument passed to fopen is invalid. My guess is here. This is incorrect. Let's see. Let's see the oops. Let's see mode. Let's see the mode R. Mode is R. R for reading. My guess is this is correct. The stream is position at the beginning. Have no permission. Okay, let's see. Embed the argument again. And optional. fopen. It should open. fopen. Restricted path. Restricted mode. Okay. Well, this is weird. You can't open the file. Maybe I will check this later on. I think there's something wrong with the open. But the usage of a file handler is just like so, like this. We can in this case our file cannot be opened, so it's null, so it's not destroyed. But I can check. We can put a diagnostic here. It's null at the instruction. Destruction. Let's see. See? So if the file is opened, we're sure that it will be closed. It will be closed. But in this case, I just got something error, so the file cannot be opened. So if the file is open, because this is not a point in this video, so I'm not going to spend more time to chase why fopen is not working. It's not giving us a valid file handle. So maybe I will look at it after the video. So the point is to demonstrate that a RAII file handle will ensure that the file will always be closed no matter what's happening. No matter whether you are raising an error like you are raising an exception like this, we can put a diagnostic here. Exception see what's happening. Unexpected error. So here, if we are using a raw pointer here, for example, oh right. Let's try allo. See? Yeah, I just changed the wrong place. There's no B character here. So I changed the wrong place. This is the one, this is the place. So see? File pointer blah 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 is closed. And we actually got an unexpected error from this function. So but the file are still be closed without any leaks. So this is the point of RAII. Why it's important. It ensures that no matter what kinds of exceptions, or if you abort it, let's try again. If we abort it, it will be fully different. It will be totally different. Let's see. Abort, let's see what. Okay. Oh, right. Wrong spelling. Okay. Compilation about chap 6. Okay, in this case, the file handle is not destructed when we call the abort. But when we call terminate, let's see what will happen. Terminate is safe. See, but terminating. So abort and terminate are danger, but not abort. Still danger. So remember this. Throw is safe. II ensures that no matter what exception is raised, the throw keyword, it ensures that the file handle in RAII resource will be released when an exception. But remember that we just tried that when it's abort or terminated, it's not guaranteed that the destructor will be called. It's not guaranteed because we just tried. You can see that. So this is why II is important. If you use the raw pointer here, and an exception is raised, then the file handle will be leaked. So this is why it's important. So okay, I think this is all for today's video. I will continue with other topics around memory management in the next video, and write more examples to demonstrate. Yeah. So okay. All right. That's all for this video. Bye.